Our next speaker is Rahul Jain, who is going to talk about split-state non-malleable code and secret sharing scheme from quantum messages. Thanks, Rahul.
Okay, so this is joint work with Naresh, Vipul, and Zhao, and I'm going to be talking about non-malleable codes in the split-state model, and also a secret sharing scheme for quantum messages. Okay. All right. So let me begin with the model. Okay. So what are non-malleable codes? So in these codes, what happens is that there is a message M, which is encoded by the encoder and corrupted by the adversary. Let's say adversary applies the function f, and then it's decoded by the decoder to get M prime. And the condition that we want is that for all M, right, the M prime that we get, like let's say a distribution on M prime that we get, is close to either M, the original M, with a certain probability, or with the rest of the probability, another distribution D, such that this probability PF and DF only depend on the adversary action F, and have nothing to do with this original M itself. Okay. So these are non-malleable codes. So broad. I mean, like roughly speaking, what they capture is that if there is any adversary acting on the corrupting the message, corrupting the code word, then either the decoder should get back the original message or something which is completely independent of the original message. Okay. Okay, and they can be thought of as relaxation of error detecting codes. Okay, and one very popular model in which these codes are considered is the so-called split-state model. And in this model, there are basically two adversaries, say Alice and Bob, and they're both, okay, so the message is encoded into two parts, X and Y, and Alice and Bob are separately, corrupting the two parts, okay, to X prime, Y prime, and then the decoder decodes to M prime. And the rate of the code is the number of bits in M divided by the number of bits in X plus Y, okay? So this is the two-split model. Okay. All right. So before we describe our construction, I will describe this another primitive called NMRE, which is a very useful primitive, and this is basically, it's related to non-malleable codes, but weaker than that, in the sense that the encoder. So in non-malleable codes, the encoder gets the message and then creates the codes. Okay, X and Y. In NMRE, the encoder, generates the code X and Y along with the message M. Okay. So, and it's much easier to construct these NMREs with much better rates. Okay. Okay. So here is the NMRE. What happens is, okay, the encoder uses some randomness to create the code X and Y along with the message M. Okay. Okay. And then, the X and Y are perturbed to get X prime, Y prime, and then we have M prime. And the rate of the code is, again, number of bits in M divided by number of bits in X and Y. Okay, so now let's get into the quantum case. In the quantum case, if we have the split-state model, what will happen is that the adversaries, Alice and Bob, will apply their respective unitaries, U and V. And at the same time, they will also have a shared state, okay? This entangled state, pure state, W1, W2, that they share between themselves. And this can allow them to have this larger class of adversary attacks, okay? So this is the quantum model, okay? A two-split model, okay? So in this other work, they present a NMRE, quantum secure NMRE, rate half, okay? And this is basically just a two-source non-malleable extractor, essentially. So and the security is that you have this M coming here and M prime, which is decoded. So the joint distribution in M and M prime is with a certain probability either MM, like two copies of M, or with the other probability, something in tensor. So M tensored something else, okay? So this is the security model. Okay, so there has been a lot of work done in non-malleable codes, especially in the classical setting. A whole lot of work, and then culminating in constant rate codes for the two-split case. And in the quantum case, where one is encoding classical message but with quantum adversaries, this work presented a 1 over poly rate two-split non-malleable code. Okay, but this was for the classical messages. Okay. Now, right. So the applications of constructing these non-malleable codes are in non-malleable secret sharing, non-malleable commitment schemes, non-malleable signatures, and so on. Okay. So what is our result? Our result is we consider the case of quantum message. Okay. So the things that I've been describing before were all classical message, but now quantum message. So how do we model this? So we have a quantum message M, okay? And the way we model is we consider a canonical purification of this message, okay? In the register M hat, okay? M hat remains untouched. M is given to the encoder, which encodes into two splits, E1 and E2, which are separately perturbed. And then the decoder gets back M. And what we want is that in this state, eta M hat is close to being a certain probability sigma M hat, so that is it's untouched, and with other probability it is something in tensor. Okay, so sigma M hat tensored something else. Okay, so this is a sort of a natural extension of the security of non-malleable codes in the quantum case. Okay. So, right. So, okay. So prior to, they had also, this work, AM17 had also considered quantum non-malleable codes. However, with shared key R. Okay. Shared key R. So this shared key is presumed to be already, going untouched from the sender to the receiver. Okay. So we can consider it sort of a two-split model, but in the two-split model, the second split, the adversary is not doing anything. Okay? So therefore, this R just goes untouched to the receiver. So in this weaker model, they had actually considered non-malleable codes, and however, their definition was also different from our definition. They had considered definition in terms of some mutual information definition. Okay? And however, the thing is that they used this classical randomness R to apply a random Clifford basically from a family of two design unitaries, and this is the way they created the non-malleable code. Okay. So this is also, this part of it that the using a classical randomness R, we apply a random Clifford to protect the quantum message is also what we do. Right, as well. However, now, okay, so before we get to the two-split case, let's consider the three-split case first for simplicity. So what is our encoding? Our encoding is, okay, so here we take this X and Y, we apply a two-source non-malleable extractor to generate R. Using R, we apply this random Clifford on this part of M. And then there are three splits, okay, the Z, X, and Y. They all go separately perturbed. And then once there is an X prime, Y prime, the non-malleable extractor is applied again to generate R prime, which then this is used to apply this Clifford back to generate M prime. Okay. So what is the overall idea here? The overall idea is that these two splits are used to protect R, okay, non-malleably, and this split is used to protect M. Okay, this is random Clifford. Okay. All right. So this is the two splits to protect R, the third split to protect the message, and then what happens is that once we're able to protect R, there are two cases, right? When R is equal to R prime and R is different from R prime. When R is equal to R prime, we are able to use these Pauli mixing, Pauli twirl, Clifford twirl, Clifford randomization properties. To appropriately decouple the message and argue the security of the quantum message in this case. And similarly, when R is uniform and independent of R prime, we again use those similar properties to argue. Basically, we are able to use these Cliffords to completely decouple the message out from the rest of the stuff, okay, in this case. Okay. All right. So those are some technical things which I won't have time to get into, how precisely all these properties of Cliffords are used here. But nonetheless, what happens is, okay, so now how to get to two splits? So the natural thing is we just combine the first two splits to make just one split, okay? So that happens, but then there are, I mean, of course, additional issues that crop up. One is that, for example, like, even this fact that, why will, once this Z is included and given to Alice, why is this even a non-NMRE anymore, right? Because the Z can potentially start to have information about R, okay? So this may not even be an NMRE. But then, what we do is we first consider the case where M is maximally mixed, okay? So when M is maximally, which is what we call the average case code. So when M is maximally mixed, what happens is that we can, firstly see that the Z will just remain maximally mixed because this is unitary. It will not depend on R. But the thing is we need even a stronger property that not just Z, but ZM hat actually is something that doesn't depend on R, okay? So for that, what we are able to do is what is this transpose, the so-called transpose method or transpose trick. That is, we are able to take the CR and actually apply it on this wire instead of this wire, okay? You apply it on this wire. If this is maximally entangled, Bell state, then you can take the CR and actually apply it here. And once it's applied here, then we can really just postpone it, right? Because then it doesn't interfere with anything happening here, okay? So therefore, this entire thing just becomes like, a neat to NMRE here, okay? So once that happens, then, and then we have to also take care of, sort of appropriately splitting the entire action V here into cases so that, we are able to handle, the case of XY being equal to, X prime, Y prime being equal to XY, X prime, Y prime being different from XY, and this V being identity on Z versus V being something else, okay? All right, so all of this happens, and then we eventually get a rate 1/11 two-split non-malleable code for the uniform input message, and using that, we are able to get a 1 over poly rate for the worst case. And then we also give this application for non-malleable secret sharing, which I don't have time to get into. Okay, so open question, of course, one natural open question is, can we give constant rate codes for in the case of quantum adversary, classical messages or quantum messages? Can we give constant rate secret sharing, and so on? Okay, thank you.
For questions. Meantime, the next speaker can come forward. Yes, Christoph.
So in the classical case, you also require that you have a simulator that simulates this distribution df efficiently given f. Do you have the same in the quantum case?
Okay, so the definition that we present here is not exactly in this composable simulator-based model, right? We're just giving it in this. But I mean, we have not. I mean, formally we have not presented in that model, but we believe that we can actually port it to that model, simulator-based. Okay. For now, we have just given it in this natural model of splitting the state into two parts, where one part is MM and the other is.
No, but the question is, this distribution df. You say for every tampering function f, there exists some probability, this pf, and this distribution df.
Yeah.
Can you sample this df given f in the quantum case? Because in the classical case, you want to simulate that actually, given f samples this distribution. That's important for some security proofs. Can you do it in the quantum case?
Meaning whether it's efficiently sampleable, you mean? I get. Okay, so that's what I'm saying. So we have not really looked in detail about presenting into the simulator definition, but I'm just presuming that because the whole okay. Yeah. Oh, sorry. Yeah.